So the objectives for this session is like this. What are the important factors which are related to cylinder lubrication in marine diesel engines? And we'll look at some of the challenges compared to lubrication in other places. What is the challenge in cylinder lubrication? And we'll take a look at some of the recent developments in this area. The principle of lubrication for any sliding bearing, the starting principle is given by this curve called Stribeck curve. In this Stribeck curve, its purpose is it explains the principle of lubrication in any bearing which comes under sliding contact bearing. Bearings usually come under two main categories. One is called rolling contact bearing, and the other one is called sliding contact bearing. In rolling contact bearings, you will have rolling elements. Ball, roller bearings, they all come under this category. Whereas in sleeve bearing, or even in the case of cylinder and piston ring, the liner piston ring movement, the lubrication is coming under this category called sliding contact. So wherever you have sliding contact type of movement, then this curve is applicable. This is called Stribeck curve. It is commonly seen in lubrication of journal bearings. The same logic applies here also. So we look at this a little bit in detail. So cylinder lubrication for the diesel engine also comes in the same category. Now, what is there on the x-axis is a value called bearing modulus. Bearing modulus is made up of these values Z N divided by P. And on the y-axis, we have the coefficient of friction. Where the friction coefficient is high, that part is called boundary lubrication. And as the friction coefficient starts coming down, it goes into an area called mixed film lubrication. And then it comes to a place called hydrodynamic lubrication. Now, hydrodynamic lubrication means there is a full oil film separating the sliding part. If in the case of a bearing, between the journal and the bearing, there will be a full oil film. And the purpose of the oil film is to prevent metal-to-metal contact. So, number one principle of lubrication in any application is to reduce friction. And to reduce friction, metal-to-metal contact must be prevented. So, how is the metal-to-metal contact prevented? Is by an oil film. And hydrodynamic lubrication means the movement of the member or movement of the lube oil itself creates the lubrication. That is the ability for the film to remain in between is generated by movement. That is why it is called hydrodynamic lubrication. So this diagram is commonly studied with journal bearings, but it also applies in the case of cylinder and liner lubrication, cylinder liner lubrication. So what are these values? Z is called the viscosity of the oil, the viscosity of the lubricant that is used. N is the sliding speed. That means the speed with which the movement takes place. And P is called it is called as a normal pressure. That is the pressure which is pressing down on the part which is moving. And it is given as force divided by area. So these are the three values. One is viscosity, second is the sliding speed. Sliding speed will be in so many meter per second. And this is the amount of force divided by the area. So if you take the case of any journal bearing also, same principle applies. And when you see this bearing modulus, whenever the value of bearing modulus is less, it means the friction is high. And as the value increases, the friction comes down and it comes to a lowest value somewhere here. So what are the changes which are taking place here? First, you look at the effect of speed on this. When there is no movement at all, remember the x-axis is Zn divided by P. So when there is no movement at all, N is 0, then the friction will be very high because metal to metal contact will be there. And there is no oil film at all which is generated. So in any bearing, including the piston ring liner lubrication, if the speed of movement is less, there will be no oil film at all. So in such case, metal to metal contact will take place, and this metal to metal contact will increase friction. As the speed increases slightly, then film will start to build up. And the film that is building up will start reducing the friction. Then we are entering into this zone called mixed film lubrication. So during the mixed film lubrication phase, oil film is building up. The film becomes thicker and thicker. And at a particular value of this bearing modulus, a full film will build up and friction becomes lowest. At higher values of BM, viscous friction in the oil film will start increasing. So if you go back to the previous sketch, it will be like this. There is no movement at all. So there is no oil film and you get direct metal to metal contact. And whatever is the friction due to that, you will get at this point. As movement takes place with oil, then the friction will starts reducing like this. And then somewhere here, once the speed has reached sufficiently high, somewhere here, this oil film become enough to support the load completely. So there will be hardly any metal to metal contact and the friction is lowest. Then why should the coefficient again start increasing after this? This is because of viscous friction, not because of metal to metal contact. It is only because of viscous friction. So as the oil film becomes thicker, within the oil film, friction will be more. So which is the position you should try to be in any lubrication? You should be here. Even though this will have the lowest friction, the chance of becoming high and wear down increasing is very high. So you don't want to be here, you'll be in this area. So a good bearing design should ensure that it is here. And in the same case applies for the cylinder liner lubrication also. You want it to be here. But the problem with piston lubrication, liner lubrication is piston does not move at a steady speed. It is at zero speed at TDC and BDC. So you are going to be constantly coming to this part and this part. So in a piston, you are constantly moving from here to here all the time. Maximum speed comes at mid-stroke. That is when a good oil film is possible to generate. In most other times, you are here in this area. That is the reason hardness of the ring material and hardness of the liner, all of them become important. Because if an oil film is capable of separating it, then the hardness does not matter. But it is impossible to prevent contact ends. That end means at TDC and TDC. Then the second part in the denominator is Zn by P. P is force divided by area. So if since it is coming in the denominator, if P increases, then the bearing modulus will be less. If the bearing modulus is less, it means you are more close to the beginning, where the oil film thickness is less. So one more important principle is, one principle is already is the movement speed. How fast is the movement taking place? And faster the movement, you will have lubrication. Second part is the amount of force which comes on the sliding surface, whichever is the sliding surface. So if the force is more, since it is coming in the denominator, bearing modulus becomes less, and lubrication becomes more difficult. So what are the ways to control this? Is since the value is pressure, it is force divided by area. Then if you can increase the area, the value of P will become less. So in all kinds of bearing design, including in piston ring liner principle, the larger the area is, then the lubrication will be better. So you can see this commonly known example, where in the cutting rod of a trunk piston engine, this cut is given at an angle. This is what we call as oblique cut like this. This oblique cut is given for the sake of making this whole diameter larger. Because in a trunk piston, when you are removing the piston, this one half of the bottom end bearing has to pass through the liner. So if I cut like this, then only half of the bearing diameter is actually passing through the liner size. This is the only size which has to pass through the liner. So if I can make this cut like this, then the entire width will be only this much. So this, assuming this is the size of the liner, then if I cut like this, then this should be the diameter. So definitely the pin of the crank pin becomes smaller. By giving an oblique cut, I can make it much bigger. So this is the number one reason why the trunk piston bottom end bearings have got a oblique cut. And along with the oblique cut comes this serrated design, because the serration is to prevent bending load on the studs. So why are we talking about cutting rod bearing when the topic is cylinder lubrication, it is for the same reason. This is a very clear example where you can see that having a large area is, or reducing the force is important. So you have this oblique cut bottom end bearings in the case of trunk piston continuum. Now, if you come to the cylinder liner, what is the force? Where is the force coming from? The force for pushing the piston ring onto the liner. The force comes from the gas pressure. The highest gas pressure will be on the first ring. This everyone understands. Then the second ring has got a lower pressure. Third ring has got a even lower pressure. But the highest pressure comes on the first ring. And the pressure acting behind the piston ring pushes the ring onto the liner. So, what is the maximum peak pressure that you are seeing nowadays? In the case of two-stroke slow-speed engines, the peak pressure reached 180 bar. This is in the latest G series engine from MA and BMW. Till recently, about 150 bar used to be the highest peak pressure. Now it is reaching nearly 180 bar. That is in a four-stroke engine, this pressure has already crossed 220 bar. There are some designs coming with 240 bar. So this is the peak pressure in the cylinder, maximum pressure. Now, why should peak pressure be so high? Now, the higher peak pressure means there is more stress on all the parts. There is more stress on the piston crown, on the piston ring, on bearings. Everywhere the load is high. Then why should you increase the peak pressure? It is for this reason. The higher peak pressure you have, efficiency will be more.
To give more power output.
Combustion. No, you don't get more power output. Power output is linked to the MEP. That is effective pressure. We are not talking of the mean effective pressure here. We are talking of the peak pressure.
Yes.
So when the peak pressure is high, it is thermal efficiency in your system is high. There is in fact a ratio between Pmax and MEP. The higher this value is, efficiency will be more. So the way to understand is MEP, if you can make it more, will improve your power to weight ratio, or what we call as specific power. Power to weight ratio will be more if MEP is high. But if increase peak pressure, then the efficiency is more. The reason for that is from this principle of an engine functioning. Idea is you burn fuel, and from the heat, the energy is transferred to the working medium. Working medium is the air which is there. So idea is the working medium should retain the energy and then give it to the piston. And the heat should not be lost to the surroundings. For this, the combustion has to be very rapid, and whenever you have rapid combustion, you will get high peak pressure. So there is a connection between peak pressure and efficiency. And efficiency is high, it means your SFOC will be less. So that is the reason engine makers are constantly trying to increase peak pressure. The limitation is the ability of all your engine components to take the pressure. So what is the way problem is developing for your cylinder lubrication is this value is becoming high. The force with which the piston ring is being pressed is becoming more and more. This problem was always there. At TDC and BDC, sliding speed is less. In fact, at the dead centers, it does not move at all. But the advantage of BDC is there is no pressure also. There is no force on the ring. But TDC, you have a serious problem. You've got piston ring which is not at all moving, and you also have very high pressure. So this bearing modulus number, if you see, it is going to be practically 0. And you have very thin films of oil separating the two metals. That is why everyone knows the wear down rate is much higher in the liner near the TDC part. The advantage that a 4-stroke engine has is that the 4-stroke engine has one TDC where the combustion takes place. It also has another TDC where there is no combustion. It is called as non-firing TDC. So in this non-firing TDC, even though sliding speed is less, the force is also less, and it is possible to build up the oil. So compared to a 2-stroke engine, 4-stroke engine is easier to lubricate. Any questions so far on this principle?
Sir, moderator here, sir, Mr. Venkatesan, sir.
Yes.
One question raised by Mr. Vishal. What is the meaning of bearing models and where it is used?
Yeah, bearing modulus number is Zn divided by P, where the value Z stands for viscosity of the oil, the letter N stands for sliding speed, the speed with which the two parts are moving relative to each other. So, for example, if you think of a journal bearing, as the RPM is high, this value of N will be high. Otherwise, it will be less. P is a number, value which comes in the denominator, and P is called as bearing load per area. Means how much is the force coming on the bearing, and you have to divide that force by area. You get this value called P. So in the graph, you can see the higher the value of bearing modulus, you will get better lubrication. So it's an important design principle of any kind of journal bearing, but it applies wherever sliding movement is there. That without a rolling element, wherever you have movement, the same principle applies. Any other question?
Thank you, sir. No other questions in chat, sir.
All right. So if we move on, in the case of a trunk piston engine, how is the lube oil reaching the trunk piston? Can any of the students answer?
By splash lubrication.
Gudgeon pin, sir.
Some oil can come out of the gudgeon pin, but the gudgeon pin is in one direction. It is not a spherical design. So how do you make sure oil goes all around the liner?
Splash oil control ring.
Splash lubrication.
Yeah. So when you say splash lubrication, how exactly is that splash take?
Through the internal borings.
Internal boring in the
Crankshaft and connecting rod.
Yes, there is an oil is delivered to the main bearing. Everyone knows that. From the main bearing, there are drill passages in the crankshaft. With that, the oil will reach the bottom end bearing. Right? What happens next? This oil which is delivered to the engine has to reach the liner. So how will that reach? One method is like someone said, from the gudgeon pin. In fact, there are now engines coming where it goes to a piston ring itself. But the most common design is by splash.
Splash lubrication.
So what do you mean by splash is It is not that the cutting rod will hit any oil or anything. There is no. It's not like there is a stagnant amount of oil in the sump, and then the moving cutting rod will touch that, and that is how it will splash. So what do you mean by splash? Is by oil coming out of the bottom end bearing. From the bottom end bearing, lube oil will escape. So whenever you can also see, whenever your priming lube oil pump is running, and if you go and open the crankcase and see, you will see oil is coming out of all the bearing. But imagine when the engine is running, then the same oil coming out of the bearing will be thrown out by the centrifugal force. So the rotation of the crank with oil coming out, that is the part which is going to splash oil onto the liner. So splashing does not mean the crank dipping into oil. It is not like that. It is because of centrifugal force. And this oil will be quite a bit. Then most of this oil will be scraped down. So you have oil scraper rings. They will control the amount of oil which will remain on the liner. And this oil is scraped down. In the case of a 4-stroke engine, there is advantages because nowadays trunk piston engines are only 4-stroke. Don't have 2-stroke trunk piston engines. So as there are 2 strokes with less pressure, the oil is spread easily by the piston ring. There are 2 strokes, means the suction stroke is there, and especially during the exhaust stroke, piston rings will spread the oil. And this oil is going back into the crankcase, and it will be treated and cleaned and all those things. So everyone knows that for a trunk piston engine, it is the crankcase oil which is used for cylinder lubrication too. Now the developments in this is there are engine designs where the oil is supplied from the piston side, from inside the piston. Apart from the gudgeon pin, it is also going to the piston. The lowermost piston ring goes to that side. Those designs are also coming up. There is also designs which is coming from outside, cylinder to, or rather similar to the faucet lubrication, through an external separate cylinder lubrication system also is there. But this only a few engines have come out with this. Now, what will be the consumption of oil is typically around 0.3 to 0.5 gram per kilowatt hour. Because some of this oil will be taken up to the combustion space, and there it will get burnt. So you can say in a well-maintained 4-stroke trunk piston engine, around this much of oil will be consumed per kilowatt hour. So what is the type of oil that is used for trunk piston? This is a typical arrangement. So you have this SMERA grade. This is the grade number. Density is like this. Viscosity is the main part. So viscosity at 40 degrees centigrade is 110 to 140. Main thing is this TBN value. So TBN is around 20 milligram of potassium hydroxide per gram. So this is the unit for specifying what is the base number in the oil. And all of you will be knowing that the base number indicates the amount of alkaline additive in the lube oil, which is meant for neutralizing the acids which are produced. Now this base number oil will be sufficient for burning low sulfur fuel. If it is a diesel engine, diesel fuel, this will be sufficient. If the engine is going to run, trunk piston engine is running on high sulfur fuel, then the base number will be even more. Probably 40 will be required. Now coming to the crosshead engine, this is where the main issue is. What are the different ways the liner wears out? One is called abrasive. Abrasive wear is due to hard particles. Wherever this topic is mentioned, it is always due to hard particles. Now, where will the hard particles come from? One is from the atmospheric air itself, it can come as sand, as an example. It also comes in fuel. Again, sand will be there, contamination by sand is there. And we've got this catalytic fines, which everyone knows. So, catalytic fines are aluminum oxide, which is used as a catalyst during refining of fuel. So, this catalytic fines will get carried over into the bunker fuel, and it can cause a lot of abrasion. Then lot of bunker fuel is also contaminated or mixed with used automobile lube oil. Then with used automobile lube oil, metal debris is also added to this. Even though ISO standard 8217 standard is trying to curb this, it is not fully eliminated. So they will still have automobile lube oil which is mixed up in bunker, and that lube oil can carry weigh down metal particles. So these are the reasons for having abrasive wear. So abrasive wear can be prevented by your quality of your system. You get very good bunker, you have good filtration arrangement, your purifiers work very fine, then this part can be minimized. But the next one is not like that. This is the main issue with liner lubrication, because most of the points which are discussed here, they are not easy to eliminate. That is how the system works. So adhesive wear is related to loss of oil film. Word adhesive means sticking. So its meaning is piston ring and liner stick to each other. So why should they stick to each other? Is because an oil film is lost. So in this case, again, this is where you go back to your Stribeck curve, where sufficient oil should be there. Oil should have sufficient viscosity. And remember, Z is the viscosity of oil. So if you have sufficient amount of oil of the right viscosity, and if the movement is there, then it is possible to maintain the oil film. If you cannot maintain the oil film, then contact will take place. Excess load, like it happens at near the firing load. And in the liner, surface will become polished. We say polished means it becomes like a mirror image, and it doesn't have the ability to hold lube oil. In all these cases, this will be a problem. So in the meaning is, once the oil film is lost, the asperity, the meaning of asperity is minute projections in the surface of the liner as well as the surface of the piston ring. They will touch and they will weld together. So that this is happening due to high contact force. So when this asperity is in the liner and the piston ring weld together, this is called as micro seizure or micro weld. And since it is a moving part, this micro seizure will break. And since at the contact where the two parts are coming together, since the force is very high, temperature also will be very high, then what happens is the products of this micro seizure become even harder. So piston ring is itself a hard material. Liner is a hard material. But when this asperities micro weld or micro seizure happens, the products of this are even harder. So this harder particle will create further abrasive wear. So there is adhesive wear itself causes wear down. In addition, adhesive wear itself will produce even more abrasive. What are the issues other than this? What are the other issues which will lead to adhesive wear or loss of oil film? One is this: the scavenge air which is supplied. If the water is not removed from the scavenge air sufficiently, then water droplets will destroy oil film. It prevents good oil film from settling. And you have this pore polishing due to carbon buildup. Carbon buildup which takes place in the top land area of the piston. So, putting all these points together, this cannot be avoided. High load in the liner cannot be avoided on the liner and the piston ring. Oil film getting reduced because of movement of the piston at TDC and BDC cannot be avoided. So there is a certain amount of adhesive wear which is likely to take place. So it's a question of controlling it. So for that, the main issues are this. Are you delivering the correct amount of oil, and is the oil in the correct viscosity? Is the entire part of your liner coated with oil? In the place with the highest load, are you able to maintain an oil film? If you are able to do all these things, then the adhesive wear will be less. So the design of the liner is that you should not have a polished liner surface. Polished means it should not be like a mirror. Instead, it should have some marks. Like we say, this mark should be like valleys. It is called. Be like this. The liner surface should have some. This is the liner surface. Oil should stay here within this part. So this portion will retain some oil if you have got this cuts inside. So there is a process called honing a liner. So when if this is a liner surface, it is like saying there will be deep scratches in the liner. The scratch will be narrow, very narrow, but they should be deep. So when you make a pattern like this in the liner, this part will hold lube oil. Otherwise, if the entire surface becomes like this, without any of these valley part, then it is difficult to maintain any oil film. That is why this is not good. A mirror finish is not good for a liner. So there's a manufacturing process called honing, and in many vessels, it is done in between also. So during maintenance at intervals, the liner can be again honed with the honing tool, and you can create a pattern. If carbon builds up on this part, which is called as this is the piston, this is the first piston ring, and this is the liner. Then in this portion, carbon can build up. This is called as the top. This area is called the top land, and if carbon builds up here, as the piston moves down, it will rub against the liner and prevent the lube oil staying there. That is called as pore polishing due to carbon buildup. So there are different kinds of polishing surface polishing which takes place in the liner, and all of them lead to increased adhesive wear. So this ring is called as a bore polishing ring, anti-bore polishing ring, or also called as piston cleaning ring. So this ring will prevent the buildup of carbon around the piston. This has been there in engine design for a long time. Both trunk piston engines and crosshead engines are fitted with this nowadays. This is one of the developments which has improved liner lubrication, so that the carbon buildup around the piston is reduced. Then the third mode of third mode of wear.
Mr. Venkatesan, sir, moderator here.
Yes.
It's time for polling, I will inform.
Yeah, please go ahead.
Dear participants, the polling, now we are launching polling. Just please free to give your valuable feedback by polling. Thank you.
Now, the corrosive wear is due to presence of sulphur oxide. So there is sulphur in the fuel, and sulphur is a easily combustible substance. So the sulphur will immediately burn, and you'll get sulphur oxide. The sulphur oxide, which is in the exhaust or combustion product, will lead to sulfuric acid formation, and the sulfuric acid will attack the liner. So in this case, to prevent corrosive wear, what are the factors which are important? It is the quantity of lube oil again is important. But apart from quantity, TBN is important. If you don't have sufficient TBN, you will not be able to neutralize this sulfuric acid. So corrosive wear, if you want to prevent, there are 2-3 points. Number one is this sulfur in the fuel. If sulfur is not there, corrosive wear will be less. And if the liner temperature is high enough, sulfuric acid formation will not be there. And if your oil has got sufficient TBN, whatever sulfuric acid is formed can be neutralized. This is a basic principle. Now, the issue that is happening is if you run your engine on low load, and if as the piston stroke is increasing more and more, large portions of the liner are in cold temperature. So this low temperature of the liner will result in more corrosive wear. Fortunately, to a large extent, this problem will be reducing, because in whichever vessel they are opting for low sulfur fuel, then this corrosive wear should come down. But as you will see, there is another issue. This corrosive wear reduction can increase the adhesive wear, or the scuffing part, that is called. One more word for adhesive wear is scuffing. Okay, so that also you should remember. So what is being told is that this change which has happened with sulfur, due to the limitation of sulfur, corrosive wear in liners and piston ring should reduce. But there is a problem with low sulfur fuel. That is, low sulfur fuel has created issues in 2 other places. One is in the entire fuel handling system. The sulfur itself is an element with some lubricating ability. So if sulfur is not there in the fuel, then when sulfur is not there in the fuel, there is a problem of lubrication otherwise. So what happens is that when sulfur is there in the fuel, then that provides little bit of lubrication in the liner also. More importantly, if you have small amounts of sulfur oxide, then slight corrosion takes place in the liner. And the slight corrosion will create a liner surface which is slightly pitted. And this pitted liner surface will hold lube oil better. So what is being suggested is sulphur in large quantity is bad, but sulphur in smaller quantity is actually better for liner lubrication, because it will keep renewing the liner surface, which will hold the lube oil. So what is happening with the low sulphur and very low, ultra low sulphur fuel is that, first of all, this liner itself wears out more. And then because of the inability to maintain the oil film, that is because the pitted surface is not there, then also scuffing is taking place. This type of scuffing is called as chemical bore polishing. That means the liner surface is becoming polished because of absence of corrosion. The other type of bore polishing, which is due to carbon buildup, is called as mechanical bore polishing. So bore polishing is something you don't want in liners. Traditionally, it was always associated only with carbon buildup. Now this low sulfur fuel is also creating bore polishing problems. So in modern systems, what are all the new developments taking place? Quantity of the lube oil that is being used, that will be controlled. TBN has been an issue in recent years because of varying sulfur in fuel. The vessel operates with different sulfur levels at different places. So this, with the sulfur cap, this variation has come down. But there are vessels which are fitted with scrubbers which will still operate with the high sulfur fuel also. So this issue will still be there. So, and the timing of the injection, that at what point the lube oil should be injected into this. And then how to control according to load. To take care of all these things, all engine makers are using only electronic cylinder lubrication. Older cylinder lubrication many years back was fully on mechanical design. Now, all the engine makers use electronic cylinder lubrication. There are different types. MA and BMW uses what is called as alpha lubrication, and Wärtsilä Sulzer uses what is called PLS, or pulse lube system. The working principle of an alpha lubricating system is quite simple. This is a piston into which cylinder oil will be delivered, and the cylinder oil which is delivered will be pumped through this. This is a small plunger, you can see. Will be pumping the oil into this, through this. So this pump is operated by this piston, and this piston is driven by this oil. So in the before ME engine came, the oil for driving this was also cylinder oil. So you can see here 45 bar cylinder lube oil is there. So there is a cylinder lube oil pump which will run and produce this 45 bar oil, cylinder oil pressure. This 45 bar cylinder oil pressure will be directed here through this solenoid valve. So when this oil is directed here, this piston will move and that will inject the oil which is being delivered through this. And the full advantage of this system is easy to control the quantity. It is also easy to adjust the timing. So the principle of timed lubrication is that the cylinder lube oil should be delivered as the piston ring pack is passing the wheels. So the idea is to deliver the oil into the ring pack. For that, timing is required. BMW always attempted timed lubrication, even in the mechanical design that was there. So timing is better. Second is it's much easier to control the quantity because the whole drive is controllable. How long you want to keep the solenoid open and how frequently you want to lubricate. All that can be controlled very easily. Of course, because this is not mechanically driven, you must have a crank angle sensor so that the actual position of the crankshaft is known. Now, from this system, because it is electronically controlled, BMW developed this system called ACC, which is called as Adaptive Cylinder Oil Control. Its logic was simple. It makes it easy for the engineer on board to control the quantity of fuel, cylinder lube oil, according to sulphur percentage. So, two main factors will be this. What is the sulphur percentage and what is the engine load? And in addition, you can also change the feed rate according to the engine wear down or cylinder condition. So it is very easy for the engineer on board to control cylinder lubrication on each cylinder according to fuel and according to engine load. So these are the rates which are recommended. If you have a 100 TBN cylinder oil, the minimum rate should be this 0.6. So you don't go below 0.6 gram per kilowatt hour. That is the minimum. Then if you're operating in sulfur like this, as the sulfur is more, then the rate is, you can set as 0.2 gram per kilowatt hour. So 0.2 gram per kilowatt hour multiplied by the sulfur. So if you have 4% sulfur, 4% into 0.2 will mean 0.8. So you can see 0.8 gram per kilowatt hour should be the setting. So this example is for 100 TBN cylinder oil running on this type of sulfur fuel. Once again, we'll repeat. There are vessels which will be fitted with scrubber and they may be operating on higher sulfur fuels within the limits, whatever is allowed. So with that, this will be the committed value. Now, based on 0.26 gram per kilowatt hour, this will be the value. So if you have 0.26, then the rate is more. So whether you choose 0.2 or 0.26 gram per kilowatt hour for this factor will depend on the condition of your liner and then what mode you are operating. So is there more maneuvering or is it less maneuvering? Or is it in the break-in period? All those. So similarly, you can see for 70 TBN lubricating oil, 60 TBN lubricating oil. For all these things, these are the figures given. So the main advantage is electronic control gives very high flexibility. But flexibility also means mistakes are possible. That if you don't lubricate correctly, you can have severe wear even now. Now, one of the mistakes made in a lot of vessels is that if it is possible to send more lube oil, it is better. Is one of the assumptions. Or say the more lube oil I send, better it is. That is applicable in the case of a journal bearing. In a normal journal bearing, there is no harm in supplying a lot of oil. But in the case of cylinder oil, there are two problems. Number one is cylinder oil is a consumable item. So definitely cost will become higher. More than that, even if the cost is not a problem, you have this issue that wear rate will actually increase due to scuffing. And this is because of this. Calcium, the TBN in the lube oil come from alkaline additives. And they are basically compounds of calcium. So these calcium additives will be left behind and they will build up around the top land, and that will lead to this mechanical board polish. So what has happened in many vessels is that if you lubricate too much, you actually spend more money. In addition, you also cost more weight. So it is very critical and important to control the quantity of lube oil that is used. The same way, if you have under lubrication, then also definitely increased wear will be there. Because if you don't give enough lube oil, definitely severe scuffing will take. So how to determine whether lubrication is sufficient? Can you do by under piston inspection? Can one of the students answer? Can you?
Yes, sir. We
Yes,
can do
yes.
it. We can do it.
But there are some drawbacks in the under piston inspection. It is because when do you do the inspection? It is after you do after you finish your voyage, after you maneuvered and you stop the engine. So during maneuvering, is the cylinder lubrication increased in every vessel?
Yes, sir. It is increased, sir. Automatically it goes up.
It is always increased.
Yes.
So that is because of the starting and stopping and running at low speed. Now you can understand, if you go back to the Stribeck curve, you can understand why during maneuvering lube oil has to be increased. It is because you are stopping and then starting again and operating at low speeds. So cylinder lubrication will be not so good. That is the reason we are increasing the quantity. So because you are increasing the quantity, if you do a liner inspection, it will give a different picture. This is not how your liner might look when it is running at full speed. So even though under piston inspection is carried out and it's been done for a very long time, that alone is not a very, it will not give you a correct picture of whether lubrication is good or sufficient. So what has happened further is this drain oil analysis is a principle that is being used nowadays. Many ships you will be doing. There is, it's also called a scrape oil analysis. Whatever is oil which is coming from the lube oil, I mean the cylinder lube oil which is left behind, that oil is taken for analysis and it is checked. Main thing you are looking for is, do you still have any additives left? So certain amount of TBN should be still in the drain oil. So if you have around 15, this is typically given for after neutralizing a higher sulfur fuel. So if you should have some amount of TBN, something like 15 to 20 should be still in the drain oil. And oil should be there first of all. And then you should not have much iron in the oil. Because iron is coming from bring wear down and liner wear down. So this are the techniques by which things are more close control is being. Some vessels have liner temperature monitoring. When you have sailed on ships with that, the temperature of the liner is also being monitored to keep a track on how it is. Then yesterday, one of the students also asked this question, that there is load-dependent liner cooling is also there. That at low loads, keep the liner at a higher temperature to reduce corrosive wear. So, in short, the basic principle is the sliding lubrication theory is there. And in all aspects, liner lubrication is difficult because it is intermittent motion and it has got high load and it is also at high temperature. So it is difficult to maintain an oil film. In spite of all these difficulties, you can imagine that from the time you fit a piston ring till you renew it. Nowadays, decarb is done in many engine or piston ring renewal is done in many engines after until like 24,000 hours. So this piston ring is able to last 24,000 hours. And if you calculate the total distance piston ring would have traveled, you will be surprised by the result you will get. Any of you can, in your time, you can sit and do this calculation. Just see, you know the RPM of your engine, you know the stroke of your engine, and you know the running hour of the engine. So running hour every 24,000 hours, if you are renewing the piston ring, you can calculate the distance traveled by the piston ring before it is renewed. And you'll find very, very surprisingly high value. So that is what our technology has managed to achieve. That in spite of all these difficulties, it is possible to prolong their life of liner and ring very long.